And welcome to Lab 4 for Physics 2212, Circuits and Capacitors. So in this lab, the purpose of it was to use the principles of conservation of energy in order to predict the behavior of circuits. And this is done through the use of an online model using multimeters to measure values of current and potential differences. And the results of this lab was that the actual values of current and voltage from the model closely match those of the formulas. And in an RC circuit, the magnitude of current is time dependent based on exponential equations. So fundamental physics equations and concepts we need to know is conservation of energy and charge. The idea that energy is neither destroyed nor created, and neither is charge, as well as the loop rule over here, that all voltages eventually cancel out within a loop. Ohm's law, V equals IR, and capacitance, which is C equals Q over V. So a few assumptions that the online model made was that resistance of wires is negligible, the resistance of an ammeter is also negligible, and that EMF is calculated through delta V cap plus delta V resistor. So for the first part of our lab, we used a simple circuit as well as an open circuit. The system was a circuit that surrounded the environment, and this will be evident throughout all following procedures. The circuit was just two 1.5 volt batteries, two resistors, and one of them was 47 ohms and the other was 100 ohms, and two emitters. Predictions is I1 equals IQ, REQ equals 47 equals 100, 47 ohms, I equals delta V over R equals that, 0.020 amps. And results, pardon me, use the wrong picture here for my gallery, but you know, we ball. It's actually 0.02 amps. Depending on the direction, it can be positive or negative. And when we replace one of the ammeters with a voltmeter, our reading was that the change in voltage was 3 volts, and that I equals 0 amps. So an open circuit with no current and potential difference across the opening equals that across the power source. 1.5 plus 1.5 equals 3. All right, this next one involved a closed circuit. All right, so to do this, we put the ends of the voltmeter at different ends within the circuit itself to get different readings. So from B to A over here, it's 3 volts. C to B, it's no volts. D to C, negative 0.96 volts. E to D, 0 volts. F to E, negative 2.04 volts. G to F, 0. H to G, 0. A to H, 0. And the overall change in voltage for the entire round trip is 0 volts, which means that this closed circuit follows the loop rule. And of course, I is equal to 0.020 amps. Once more, current showing up wrong on that one. And the ammeter reading doesn't change throughout the entire process, which means the voltmeter has very high resistance. No current flows through it, and the path is essentially unaltered. And here's our potential graph for the previous potential difference. As you can see over here at point C, it begins to drop through the resistor, and then D to E, no change, and then from E to F, there's a severe drop, followed by 0 volts throughout the rest. So for a parallel circuit, we connect to the ammeter in parallel with a 100 ohm resistor. And this increases the circuit to 0.06 amps since less current comes in contact with the 100 ohm resistor. And using Ohm's law here, I equals VR, we got that R for the 47 ohm resistor is 48 ohms. R for the 100 ohm resistor is 102 ohms. R for the wire is 0 ohms. R ammeter is 0 ohms. And the current is higher than expected due to the low position of the ammeter. For an RC circuit, we set up the circuit like this, just a 10 ohm volt, followed by a 20 ohm volt, followed by a 9 volt battery, and a 200 MF capacitor. Battery is attached to a 10 ohm volt capacitor in a series circuit. The bulb starts out bright, then increases until burning out. And when the battery is disconnected, the bulb once again shoots up, then decreases luminance. And here are the calculations for the 10 ohm bulb and the 20 ohm bulb. So using a plot of the natural log of change of voltage over the initial voltage change, and using this little funky formula right here, we find this relationship for the natural log and time, showing there is in fact a time dependency here. Calculating our previous data. If we divide -1 by the slope of the graph, this gets us 6 seconds, which the experiment's RC. And you get the same result by multiplying 200 MF times 330 ohms for 6 seconds. So that means the calculated RC matches the actual value for RC. Discussion, there were no model discrepancies nor sources of error. This is a perfect model, no human error. I'm literally incapable of making error in this lab. What if we were doing this lab in real life using an actual ammeter? Well, a real ammeter has non-negligible resistance, so the currents would be slightly lower. And a similar issue would occur if you use a real battery to charge a real capacitor. The capacitor was still charged and it discharged very quickly, but not instantaneously as it did in simulation where the wires had zero resistance. In real life, the wires have a non-negligible amount of resistance affecting the rate of charge/discharge of the capacitor. Thank you for watching. Please have mercy upon me on the rubric, and I hope you have a wonderful night.